So, good afternoon, everyone. Today is the eighth live class on numerical methods for engineers, and we'll get started. So, today we are going to learn on numerical differentiation. So, let's understand why do we need numerical differentiation and what is it basically. So, as we have learned in school, the kind of differentiation we have come across in school, suppose let's take an example of dy by dx. Okay, so we are given a function y equal to something, the simplest function we can think about now, probably y equal to x square, and we are supposed to differentiate it and find out dy by dx. Okay, so how do we do it? How did we learn it in school? So we basically learned that dy by dx, there were formulae, a lot of formulae that we had come across for differentiation. And here dy by dx is equal to 2x. Okay. So this is what we had done in school. But what if the function that is available to us, that is in this case the example we took was of x square, what if this function is complicated to a certain level such that the analytical expression of this function, which is to be differentiated, is suppose known, we know it, what is going to be the analytical expression, but to perform that analytical differentiation as we performed here, that when it is x squared, we differentiate it and get 2x. Probably this analytical differentiation is either difficult or it's complicated to a level that it is impossible. Okay. So when we are dealing with real life problems where suppose our function is not in the form of y equal to x square, but it is of a complicated format to capture the physics of the system, what if the equation is complicated enough? So we might not know their analytical differentiation form. In those cases, we will move ahead and apply numerical differentiation. Okay. So before we dive into the algorithm and the derivations and so on, we'll just take a few moments here and understand what are we basically doing in numerical differentiation. Okay. So as we wrote previously, suppose y is equal to x square. What we are actually interested in finding out is dy by dx, right? Now, what is basically dy by dx? Let's understand that. So dy is basically some change in y and dx is basically some change in x. Okay. So when this change is very very small, we go ahead and write it as dy, and change in x, delta x is very very small, we go ahead and write it as dx. Okay. So delta y by delta x basically means some change in y. So let's take the second point minus the first point in case of y divided by the second point minus the first point in case of x. Okay. So this is precisely what we will be doing in numerical differentiation as well. So in order to understand the procedure of numerical differentiation, what we will learn is a technique known as finite difference methods. Okay, so these are called finite difference formula for numerical differentiation. Now, what will be our approach to do this finite difference, to derive the finite difference formula for numerical differentiation? We will basically approximate the derivative at a point that we are interested by using the values of these neighboring points. Okay. So just like when we were understanding, we took this example of y2 minus y1. So suppose the previous y value and the next y value, y2 minus the previous y value y1. Similarly, here what we do is we just consider neighboring points whose with respect to the point at which we want to find out the derivative. Okay, and what we basically use is Taylor series expansion. Okay. So today we will focus on the finite difference formula only for first derivative. Um, we will only focus on the finite difference formula for first derivative. And in this case, let us first understand what is happening in this graph, okay? And slowly and gradually we will go ahead and derive the formula for finite differences for numerical differentiation, okay? Suppose this is the curve that we have, basically the function f of x, okay? And we have labeled 3 points. One is, let's start with xi, which is the point at which we are interested to find the numerical differentiation. And a point previous, just a point before xi that we have labeled as xi minus 1. And a point after xi which we have labeled as xi plus 1. Okay. So as we saw in the algorithm that we are interested in finding out the numerical differentiation at the point xi with the help of its neighboring points, right? Hence, the neighboring points that we have selected are xi and xi minus 1 and xi plus 1. Okay. So, relatively, the function values at those points are going to be f of xi for xi and f of xi minus 1 and f of xi plus 1. Okay. So let's keep this graph in mind and let's start the first derivation for 2-point backward difference formula. Okay. So what does 2-point backward difference formula basically mean? We'll take an idea from the graph first. So what we are basically trying to do here is that we are ultimately trying to find out the derivative at this point, xi only, okay? But in order to find out this point xi, in the backward difference formula, we are basically using the point xi minus 1 and xi. So we just move one step back from xi and we use the point xi minus 1. And we take the function values relative to them. So we take the function values f of xi minus 1 and f of xi. Okay. So we will see how the derivation goes in that case. So in order to proceed, what we will basically do is we will find out the value for xi minus 1 with the help of Taylor series. And the value of h, that is the difference in the x value in which interval we are trying to compute the numerical differentiation, is basically xi minus xi minus 1. Okay. So how do we compute the value of the function f of xi minus 1 with the help of with the help of Taylor series expansion? For f of xi minus 1, it is going to be f of xi minus the difference h times f dash of xi plus 1 by 2 factorial h square times f double dash of xi minus the pattern repeats, okay, for higher order terms. Now let us consider only linear terms and let's not go beyond the second derivative from here. Let's cancel all of the terms after that, but this particular term let us consider as remainder in order to understand the error which will be associated with the fact that we stop the series at this point or we truncate the series at this point. Okay. Now let us rewrite it with the remainder only. That is, it will be f of xi minus 1 will be given as f of xi minus h times f dash of xi. This is what we are interested in finding out, plus the remainder term. Okay. So we rearrange and write it such that we have f of f dash of xi on one side, and we rearrange it and write it in this manner, that f of xi minus f of xi minus 1 divided by h. Then we will divide by h throughout this particular equation. Here h square will reduce to h. Okay, and we are not interested in this entire remainder term, but what we are interested in is understanding that this truncation error will have which order of error. Okay, so since this h value is something we can determine, it is in our hand. So it basically means if we are trying to find out the derivative at xi, the point that we will consider, the previous point that we will consider, it is in our hand to uh, take how far from xi do we want xi minus 1. So this h value is basically in our hand. Okay, so we want to reduce this entire remainder term with by understanding which order of h does it depend on. Okay, so we simplify and write this entire expression as f dash of xi is what we are actually interested in finding out, equal to f of xi minus f of xi minus 1 divided by h, and the truncation error has the order has an error of order h. Okay, h to the power 1. Let's keep it like that. So simplifying it further, we get that f dash of x can be written as y dash is equal to yi, that is the point at which we want to approximate the derivative, minus the previous point divided by the difference that we had chosen plus the truncation error. Okay, so this is how we come at the formula for um, backward difference, 2-point backward difference formula. Okay. Similarly, if we instead of taking this previous point that we had taken for now, xi minus 1, we can also approximate the derivative at xi with the help of xi plus 1. Okay. So let's see, it's a very similar process how to find out the derivative for xi minus 1, xi plus 1 with the help of xi plus 1. So what we basically call it is the forward difference formula. Okay. In order to compute the forward difference formula, we have to first go ahead and find out what will be the expression for f of xi plus 1 with the help of Taylor series expansion. Okay, so f of xi plus 1 is going to be f of xi plus h times f dash of xi plus 1 by 2 factorial times h squared f double dash of xi plus 1 by 3 factorial, and the pattern follows. Okay, we will do the similar steps as we did for backward substitution, and we will again approximate this particular expression neglecting all higher order terms and considering this particular last term as the remainder to understand the order of the error. Okay, so what we will do now is again rearrange and write down f dash of xi will be equal to f of xi plus 1 minus f of x, okay, divided by h, the difference that we have chosen, plus the truncation error. So again we see that when we divide the entire expression by h, the truncation error reduces from h squared to just simply h, right? So the simplified formula even for forward difference is y dash of xi is equal to y of xi plus 1 minus y of xi divided by h plus the truncation error belongs to the order of h to the power 1. Okay. So this was about forward difference formula. Now, if we go ahead and understand central difference formula, it is very similar to backward and forward, but there is a subtle advantage that we have in case of central difference formula, and we will see that at the end of the class. Okay, so in case of central difference formula, um, first we need to derive, write the expression for f of xi minus 1 and f of xi plus 1 with the help of Taylor series expansion. Okay, so as we have written both of them in our previous method for backward and for forward difference formula, not explaining the expression again, but this is how you will write it. In case of central difference, what we basically do is after writing it, we subtract these two. Okay. And then when we subtract these two, these are the two terms that will vanish, and these are the two terms that will be added. Whichever is minus will become minus minus plus, so this will be added, this will be added. Okay. In case of central difference formula, we are considering up till this level and ignoring all other higher order terms. Okay. So what we basically get is twice of this plus in this term you can write it either as xi or as eta or zeta. So this basically varies from textbook to textbook, but you can very well write it just xi only. So our main aim of writing this this last step is to estimate the error only. Okay. So when we will rearrange and rewrite for f dash of x, what we will basically get is it will be xi y of okay, I'll explain with this one. So what we'll basically get is y dash of xi is going to be y of xi plus 1, the bigger term, minus y of xi minus 1 divided by 2h. This is the term that we have in our denominator, plus you will notice that when all the terms we divide by 2h, here also it gets divided by 2h and the order remains to h squared. I mean the truncation error is of the order h squared. Okay, once you perform the derivation, you'll be able to understand. So this is our formula for central difference formula for numerical differentiation. And so what we have done so far is in order to understand differentiation, and in case we have such kind of functions in which the analytical expression for the differentiation is either difficult or it is impossible in some cases, we have learned how to do numerical differentiation of just first order. And how do we do it? With the help of three techniques, that is backward difference formula, forward difference formula, and central difference formula. Okay. So with this derivation, now let's go ahead and sort of get a graphical interpretation of the three and understand why some of them may be a little more accurate or some of them may be a little less accurate than the others. Okay. So in case of the graphical representation of the first one, let's try and look at what we had done in backward difference formula. Okay. So our main aim in backward difference formula was to take 2 points xi and xi minus 1, okay, and try and approximate the derivative at xi. Try and approximate the derivative at xi. Right? So let's take a moment and understand what is actually happening in the graph when we are using the backward difference formula. So let's zoom into this graph. Take some other color. Okay. So this is the function, and we want to estimate the numerical differentiation of this function at the point xi. So when we directly, if the function is simple enough and we are able to directly find out the value of dy by dx, graphically what we are basically computing is the slope of the tangent, right? So now take this green line over here is the tangent at point xi, okay. So when we directly compute dy by dx and get some analytical expression, what we have basically done is computed the slope of the line, that is the tangent. So here there will be a slope of the tangent, okay. So that is basically the green line in this case. But what we have done with the help of the backward difference formula is actually we take these 2 points xi, xi minus 1 and xi, and join them with a line, okay, so and extend it. So that is this blue line. Not a good color combination, okay. So we join them with a line and extend it, and we find out the slope. We approximately try and find out the slope of this blue line, okay. So can you now zoom in and sort of appreciate the fact that there is a subtle difference between the blue line and the green line, okay. It is fairly close enough, and hence the technique sort of works. So this basically means that if we go on decreasing the value of h, if we take smaller intervals in which we are considering 2 points to estimate, to approximate the value of the different numerical differentiation, these two lines will actually merge at that point, and hence you will be able to find out a more accurate answer for the numerical differentiation, okay. Similarly, with the same concept, so this was for your backward difference formula. Okay. Similarly, let's go ahead and understand what is happening in the case of forward difference formula. In this case, so we again take this particular green line, which is the tangent at the point xi, and we take two other points this time, which is basically xi that is the point at which we are trying to find out the derivative, and xi plus 1, which is the forward, I mean in the next point as compared to xi. So we again do the same and we just connect these 2 points and extend it in order to find out the slope. I mean, we just connect these 2 points and yeah, we extend it. And by the formula that we had written down, that is derivative at xi basically equal to the y value at the forward point minus the y value at point xi divided by the difference between them, which is basically h. Okay, so you take the difference of these points on the y-axis and you take difference on the x-axis. So what you again basically do is you compute the slope of the blue line. Okay. Again, if you see that there is a subtle difference between the slope of the red line, I mean between the slope of the blue line and the green line, but they sort of tend to merge if you again take a smaller difference. Okay, so as you have noticed in case of both backward and forward difference formula, there is a difference between the slopes of the lines, I mean slope of the tangent at the point we are trying to estimate the numerical derivative, and the slope of the line that we have formed by joining the 2 points. Okay. Now we'll see what happens in case of central difference formula and why is it a more accurate method of finding the numerical derivative. So this is the central difference formula. And in case of central difference formula, if you see what is basically happening is that again the green line is the slope of the tangent, and the blue line is the line connecting the 2 points. Which 2 points? In this case, xi minus 1 and xi plus 1. Okay, and even graphically it is possible to appreciate the fact that these two lines are uh, almost parallel to each other. So you see that either you compute the slope at exactly the point, that is what the tangent is doing, that you would be able to do if you had the numerical, I mean the analytical expression for the numerical derivative, I mean analytical expression for the derivative. And if we do not have that, then we are trying to estimate by the central difference formula, which is obtained by joining these 2 points and getting the blue line. And the blue line slope is almost similar to that of the central difference formula. I mean, to that of the tangent of the tangent at the point where we want to find out the derivative. Okay, and hence the central difference formula is more accurate with respect to the forward difference and the backward difference. So this is basically the graphical representation as to what we find out by the formula of forward, backward, and central difference. And these are 3 techniques that we have learned today in order to compute the numerical differentiation. Okay. So this module is fairly simple because this is one of the foundations that we require in order to proceed on to the next chapter that we have, which is ordinary ordinary differential equations. So ODEs are one of the most important modules that we are going to learn in the upcoming classes. And in order to understand how ODEs, how to solve them, what are ODEs basically, and in what physical cases are you going to encounter ODEs, for that we need to understand what basically happens in a numerical differentiation, because solving ODEs is at the end of the day differentiation itself. So differentiation in some parts, integration in some parts, and hence the syllabus evolves in this way that we first learn the numerical derivatives and then numerical integration. Differentiation and then numerical integration, and then we move on to ODEs. So in ODEs, we will be seeing how we address a problem with respect to initial valued problems, where we are provided with the initial conditions and we are expected to find out the behavior of the function. And a little bit moving forward, we will go ahead and see boundary valued problems, where we are not given the initial, but we are given within a particular interval what is the how does the function behave. So with that, we are going to compute the behavior again. But in order to understand all of these next concepts, the basics lie with this numerical differentiation and numerical integration. So we'll keep it to this for today's class, and we'll meet again next week, Saturday at 3 p.m. Thank you for listening, and see you all next week.